take out your graphing calculators, and if you have a TI-84 or a TI-83, set your window from negative 9.4 to 9.4 and negative 6.2 to 6.2. If you have the new fancy color version, the CE version, set your window from negative 13.2 to 13.2 for your X values. And once you've set your window up, I'd like you to graph this. And we're going to look at 3 different groups of graphs today that are all rational graphs, where you have a polynomial in the denominator and a polynomial in the numerator. If you've set up your window correctly, when you graph it, it's going to look like a straight line, but if you look carefully, there's a hole in the line. So you can put arrows on the end of your sketch, and you should notice a hole in your line. So have you set your window up from negative 9.4 to 9.4? No, if you don't set your window up to that scale, it won't show up. And if it's not showing up on the negative 9.4 to 9.4, you've got a newer calculator. You've got to do it from negative 13.2 to 13.2. That's a graph with a hole in it. And we could label that hole. That hole happens to be at negative 1, negative 2. And we're going to find out algebraically how we would find that hole. But right now, you're just going to estimate it by looking at the graph. So sketch the other 4 graphs as well. So some of these graphs have holes, and some of them have asymptotes. So what we're going to do is, for the ones that have holes, we're going to draw the hole where they appear and label them. This one happens to be at negative 2, negative 3. This one has a hole right here, happens to be at 2, 4. And these other ones have asymptotes. So we're going to draw our asymptote in there and our asymptote in there and label them. This one's at x equals 1. This one's at x equals negative 2. Now this is group 1. One of the things that we're going to look at is, what do all of these equations have in common? And then we're going to describe some of the characteristics that come with them. Something that's interesting in the second and the third one on this side is we can actually draw diagonal asymptotes as well. And these are going to have a special name. They're called oblique asymptotes. Yeah, diagonal asymptotes, that makes your day? Yeah. You're like, oh great, what next? Yeah, we're going to have to find the equation of it. So, what's in common with all of these? What makes group 1? How would you describe the equations of each one? And what do they have in common? Can you see that in group 1, there was always a parabola on top and a line on the bottom. Okay? And group 1 can be described as anything that has a bigger degree on top. Have to put something on the bottom. So when I look at this rational equation, I have x squared minus 1 over x plus 1. Okay? I have a degree of 2 on top. The degree is the highest exponent of the largest power. And a degree of 1 on the bottom. So the degree is bigger on the top than it is on the bottom. Its characteristics is you either have a hole or a vertical asymptote with an oblique asymptote. Oblique is just another word for diagonal. So those are our two characteristics. The question is, how do we know if our non-permissible value is going to be a hole, or if our non-permissible value is going to end up being a vertical asymptote? Because those are the two things that non-permissible values can turn into. It's either going to end up as an asymptote or as a hole. So let's look at our equations. And one of the things that we're going to find out when graphing these equations is that it's going to be the easiest to graph if you can factor it completely. So in the first one, can you see anything you can factor? Yeah, the top is a difference of squares, so we'd have x plus 1, x minus 1. And what do you notice? These two simplify. So when your non-permissible value simplifies or goes away, then you're going to have a hole in your graph. And if I write what my new equation is as a result, I just have y equals x minus 1. What kind of graph is that? Straight line, right? What's its slope? 1. What's its y-intercept? -1. Does that look like the graph that we have? We have a straight line with a slope of 1 and a y-intercept of -1. Good. But where does the hole, how do we find where that hole is algebraically? Well, what would happen if I plugged in -1 in for x? What would y be? -2. That's the coordinates of our hole. So even though our non-permissible value disappears, and we get something that we can always graph, right? It still has a hole in the graph because -1 is still a non-permissible value. Because your non-permissible values are based on your original function. So even though you can simplify it, when you go back to your original equation, -1 wasn't allowed. They're the same thing except for the hole. This one has a hole, this one doesn't. Yes? If I plugged in -1 into this one, I would get -2, right? And that would be the coordinates of the hole. Because that's the point that's missing, because -1 was non-permissible.
And we're assuming that 0 over 0 is 1, which is not true.
0 over 0?
We assume that 0 over 0 is 1, but it's not true.
How do we assume 0 over 0 is 1?
Like, you can't assume that. That's not true. But like, the way I'm doing it.
Oh, yeah, we're assuming 0 over 0 is 1, which was what makes it simplify, right? But it does show where the hole will be.
0 over 0 is not 1.
No. Yes? If this was x minus 3, then 3 would have been your non-permissible value. Well, if -1 was still your non-permissible value, that's what you're going to plug in. Let's look at another one from here with a hole. Let's look at this one, because it is slightly different. So if I factor this, and it does factor, I have an x plus 2 on the bottom. The top factor is to be x plus 2, x minus 1. And so these simplify again. And after it's simplified, I get the exact same equation that we had in the first one. I get y equals x minus 1 again. But now the non-permissible value is at -2. So if I plug -2 into the simplified version, I would get -3, and that's how I algebraically find out where the hole is. Yes? We can't divide by 0. So I look at my original function and say, what would be not allowed? I have an x plus 2 in my denominator. I can't plug in -2 because then I would divide by 0. And of course, your graphs would have arrowheads on the end. Now in the third one, notice that the top can't be factored. Nothing simplifies, and because it doesn't simplify, we get a vertical asymptote. We don't get a whole. Same thing in the fourth one. This one we can factor. Can you see that the top could factor to x plus 1, x plus 1? But after factoring, nothing cancels out, so we don't get a whole, so negative 2 stays a vertical asymptote. Yes? We haven't figured out how to find a diagonal asymptote yet. We will, but not yet. The vertical ones are based on your non-permissible values. So here my non-permissible value is negative 2. So my asymptote is x equals negative 2. Because it's a non-permissible value and your graph can't equal that. So all your non-permissible values are either wholes or vertical asymptotes. What is going to happen is you're going to have to graph these without your calculator. So this part here is leading us to certain kind of patterns to figure out how would we graph these. Okay? So if you had y equals 2x squared minus 4x over x minus 2, how would you know to graph it like this? Well, you would factor it first, and there's a common factor of 2x that I can pull out of the top. And then I would notice, hey, those factors are identical, so they simplify. I still have a non-permissible value of 2, but now I know that at 2, it's going to be a whole. And when it's simplified, it's just y equals 2x, which is a straight line, which is drawn here. But it has a whole at 2. If I look at when I plug in 2 into the simplified version, I get 2 comma 4. That's telling me the coordinates of my whole at that point. Okay? So this is group 1, where the degree is bigger on top than on the bottom. Sometimes you get cubics divided by parabolas. You get parabolas divided by lines. Something where the degree is bigger on top than on the bottom. Now we're on group 2. The second set here. Whoa. How did you do? Draw in your asymptotes. And label them. Now, all of these ones have vertical asymptotes, and the vertical asymptotes are exactly where your non-permissible values are. These ones also have horizontal asymptotes. So how do we figure out where these horizontal asymptotes are going to be? Okay? And we can label them. This one's at y equals 3. This one's at y equals 1. This one is at y equals negative 2. And you might have been able to label them just by zooming in and looking at your graph carefully. Now, horizontal asymptotes, they occur when your x values get very large or very large negative numbers. So if we're looking at these equations, what's going to happen when you have very large numbers? Now, something that comes into effect here is, in this case, I have an x minus 1 on the bottom. So if we think about money, and 1 is $1, right? If you were, you collected money and you just barely scrounged up enough money to go to the vending machine to buy a drink. How much are the drinks in the vending machine? $1.25? $1.25 to $2, okay? So you barely get your $1.25, you got just the right amount of money. Somewhere along the way, you walk from here to the vending machine, you lose $1. That's awful, because now you can't buy the thing in the vending machine. So when the numbers are small, losing that $1 is really important. Okay? But if you had a large amount of money, if you were someone who's the richest person in the world right now, it's not Bill Gates. I think it's the Amazon guy. Anyways, Amazon guy, if he's walking down the street and he loses $1,
What if he doesn't have cash though?
not a big deal.
I don't think he carries cash.
Probably doesn't carry cash. He probably is like, what's this in my pocket? Ugh! Throws it away. Okay?
His suit's made out of money. So.
And so, the key though is that as x gets really, really big, that -1 really doesn't matter anymore. In fact, if you just look at the highest power on the top, which is a degree of 1, and the highest power on the bottom, which is just the degree of 1, which is x, what happens when you do 3x divided by x? You get 3. What about the second one? What's the highest power on the top? X squared. What's the highest power on the bottom? X squared. What happens when you do x squared divided by x squared? If you ignore the numbers, you get 1. Well, you ignore the numbers because if x was really, really big, minusing 1 and minusing 4 wouldn't make much of a difference. 6 trillion minus 1 divided by 6 trillion minus 4 is approximately, well, if you round to the nearest trillion, 6 trillion divided by 6 trillion should be really, really close to 1. It won't be perfectly 1, but it will be close to 1, and that's why it's an asymptote. It approaches 1. Because when your numbers get big, that -1 and that -4 don't make a big difference. So this one here, the highest power on top is -2x. Highest power on the bottom is -x. If you simplify that, you get y equals -2. So that means as x gets really, really big, like if you put in 1,000,000 for x, you'd have -2 million and a tiny bit, divided by 1,000,000 minus a little bit. Be really close to -2 million divided by 1,000,000, which gets really close to -2, which is why that asymptote is there. What happens if the highest power of x isn't the same? So that's sort of like what happened on our first part, right? The highest power on the top was an x squared, and we didn't have any x squareds on the bottom. We don't have any horizontal asymptote. Okay? That's a different group. So this group, what would we characterize this group as? The same degree. So you have the same degree on the top and the bottom. The characteristic then is that will always create horizontal asymptotes. These ones also had vertical asymptotes because they had non-permissible values. But your non-permissible values will either turn into holes or they'll turn into vertical asymptotes. So if you have the same degree, then you have horizontal asymptotes. So group 1 had a bigger degree on the top. Group 2 has degrees the same. Here's group 3. Here are the first 3. And we can put in the asymptotes. This one has an asymptote here. This one has an asymptote here and here and here. This one has an asymptote here and here. And if we go to the last 2, asymptote there and there. And ooh, here's one where the graph went through the asymptote. I know that feels a little bit wrong, but it's a horizontal asymptote. It's allowed. Just did it.
So the asymptote, there's no asymptote here?
The asymptote, horizontal asymptotes talk about end behavior. They're drawn all the way through, but they're really there to describe what's happening when there's big x values or big negative x values. Okay? I'll go back to the first ones, and we will talk about them. Group 3. If group 1 had a higher degree on top, group 2 had the degrees the same, how would you describe group 3? Confusing. We have a bigger degree on the top, on the bottom.
How is the other one happy with the other ones?
I don't know. Sad because the lesson's almost over and you have to go home.
Oh, that's happy.
So, what is a characteristic whenever you have a bigger degree on the bottom? You have a horizontal asymptote. And it's always at y equals 0. In fact, you can kind of use a similar argument to looking at the highest power. But now you look at the highest power in the entire fraction is the x squared. How many x squareds do we have in our denominator? 1. How many x squareds do we have in our numerator? None. What's 0 divided by x squared? 0. What's the highest power in the second one? X squared. We have none on the top. 0. 0. And so what happens as x gets big, okay? So let's look at the easy ones first. Let's look at 6 over x squared plus 2. As x gets big, can you see that the bottom of your fraction is big? So even after your brownie picture went viral, you went back down to the cafeteria, you bought 6 more. And now you have 6 brownies to share with 2 million people. They're still not going to get very much. Just a crumb. And by the time you bought the 6 more brownies, you go look, and now there's 18 million people that want to share. And it just keeps getting bigger and bigger. It's going to be next to nothing that everybody gets. Okay? Now, when we look at these examples, if we look at the 4x over the x squared plus 1, the very last one, right? If someone said, here's $100, you have a choice. You can either take that $100 and multiply it by 4, ooh, $400. Or you can take that $100 and square it and add 1. Ooh.
1,000 and $1. 10,000.
10,000 and $1.
Yeah.
Okay, so the squaring got bigger than the timesing by 4. And if the number was even larger, like a million, 4 times a million, well, that'd be 4 million. A million squared, really, even if they didn't give us the $1, even if you just looked at the million squared, that would be huge.
I'm not interested.
So as x goes to infinity, the top is infinity, the bottom is infinity, but the bottom's infinity got bigger faster. And so it gets close to 0.
Why are we talking about infinities that are bigger than other infinities?
Well, because some infinities are bigger than other infinities. Or the speed at which it reaches infinity is faster. X squared gets to infinity, gets to bigger numbers faster than 4x. And so when you divide this, this gets close to 0. So if we would characterize our last one, we always have an asymptote at horizontal asymptote at y equals 0. The only time we didn't have horizontal asymptotes was in group 1, right? In group 1, we didn't have horizontal asymptotes. What's the highest power in this one? X squared over x minus 1. X squared. How many x squareds do you have? You have 1 on the top and you have none on the bottom. If you simplified that, that's not possible. That's going to tell you there's going to be no horizontal asymptote.
Can't you just make it an X reveal? Can't because it's the one.
The X over.
It goes to x over 1, but we're going to look at how that tells us the slope of this line. But how do we find the y-intercept of it?